Welcome everybody to the second lecture, Databases and Information Systems, in the winter semester 25-26. Sound is a little bit different today compared to last week. Weather apparently makes a big difference. So we have to close the doors because otherwise it's crazy loud. If you can explain that to me, I don't really understand it. Last year it was sunny and stuff and you could just open everything. Today it's just super loud, so we have to watch CO2 levels. I will say something about your experiences with the first exercise sheet, inverted index, about your tutor, and contents today is ranking and evaluation. And the exercise sheet, I will talk about it more in a minute, is about how to get ranking right. So for the first exercise sheet, you had some very simple ranking. You just used the order of the documents in the file we gave you. Now we do more sophisticated ranking. And there will also be a small competition. Robin, do we have the table already linked? I will also show it in a second, in a minute. So here's feedback. It's just excerpts from your feedback. It's halfway, somewhat representative, so I try to pick the positive, the negative, the interesting ones, but yeah, cannot be 100% representative, of course. And thank you for your feedback. It's always very interesting. I really liked, and very interesting for us, and I think also for you, I really liked the lecture and the exercise sheet. Nice, gentle introduction back into study mode after the break, so we also feel that way. There's always this long summer break, and then you have to get back into a working mode, or at least a different mode. We, of course, are working all the time. The first lecture was easy for me, nothing really complicated. That was also our intention. Ich finde es toll, dass die Übungen optional sind. This is German, by the way. So Übungen, exercise sheet are optional in this semester. Some people wrote that they actually find it more motivating if they are optional. I think that's an interesting idea. So if you are forced to do it, it kills a little bit your motivation. I can understand that. If it's optional, then you are more motivated. I like the lecture, and especially that it's uploaded on YouTube. I only want the points and a haiku rating my performance. The coding part was a bit boring to follow. I think only one person said that. I would be interesting to know if that's just a minority opinion. Usually people like or even love the live coding, but times change, so if more people feel that way, let us know, and we don't have to do it. War für mich recht schwierig, wieder reinzukommen, so difficult to get back into stuff again. And that was an interesting comment, last one for this slide. Sometimes I wish the first exercise sheet was more difficult, so that I would not start every semester illusionized and only realized at the end that I'm stupid or whatever. Of course you are not stupid, but so the feeling is when the first exercise sheets are very easy, then you feel, oh, I can do that, and then it becomes harder, and then, yeah, so some people would like the shock right at the beginning. I'm not sure whether we want to do that, but I understand the sentiment. So let's look at some of the, so exercise sheet 1 was to build a very simple first search engine, and many of you like that, and then try a few queries and see what works, what doesn't work. And let me just go to the master solution real quick, which is also linked on the, so after the deadline, so it's here. So the master solution is linked here on the wiki. So here you have the code and so on. So please look at it if you want to check. Of course, if you ask for feedback, you will also get feedback from your tutor. But feel free to look at it, how it's ideally done or what a good solution looks like. And here it is, and we can just run it. And that's how it works. So it just reads. And now we can ask some query. And let's just try some. So here's some queries that worked well, and let's very briefly, also as a motivation for what comes next, see which queries work well and which don't. So let's type Oppenheimer. You would of course expect that you get that movie at the top, and you do. Why do you do Oppenheimer as a very specific word, and the movie is ranked very highly? And we just had this ranking where the most popular movies just come first because we already ranked it that way in the input file, so that works nice. Indiana Jones also worked, so these were all your queries from your feedback. So you get all the Indiana Jones movies. Raiders of the Lost Ark doesn't have it in the title, but it's, you see it here in red and bold in the text. So Indiana and Jones are somehow specific enough so that you only get those movies and nothing else. So first 3 hits are perfect. Gothic horror, Burton, it's another one. Let's try that one. Gothic horror, also very specific words. Burton, Tim Burton is a famous director for these kinds of movies. So we have Beetlejuice, Sleepy Hollow, and Dark Shadows. So Gothic horror, and just because you have a word in the text doesn't mean that it means what you intended it to be, but in this case it does. So it's really Gothic, it's horror, and it's by Tim Burton. And for all of them. So all 3 of them are what you expect. So these were good examples, or examples that worked as expected. Here are some that didn't work as it's expected. So somebody typed bomb and expected Oppenheimer, but got Dr. Strangelove first, because Dr. Strangelove, very famous movie from Cold War area. You should watch it if you haven't, it's really good. And it just comes first because it's... and you don't see Oppenheimer at all. So maybe it just doesn't mention the word bomb. So you expect the word in the description. Maybe it mentions a different word. It's not even in the top 3. That was one example. Toy Story. If you type Toy Story, you would expect that you get the Toy Story movies. But that was a common thing. You actually get Finding Nemo first. Why? Because it mentions Toy Story, because Toy Story overtook it in some ranking, and you get it first because it's ranked higher. So I think just already by playing around with a simple search engine, you understood that this ranking stuff is actually really hard, and I will talk more about this later. It's the topic of the whole lecture today. So getting a good ranking, getting what people expect, it's really, really hard. British Western, so you would expect Western from Britain. Let's just try that too. And just to get, so what can go wrong? So actually, what do you get? You get No Country for Old Men, which is kind of a Western, but it's an American Western. And you do get British here, but because it won British Film Awards. So you have the word British and Western, just not in the combination that you expected it to be there. And also here, Brokeback Mountain, very neo-Western. Okay, again, it got some British awards. So you don't get any British Western at all. It's just Western which won British awards. And one more, I think, Iron Man. Okay. You expect the Iron Man movies, but I think you get Avengers first, because Iron Man is kind of related. 12 Years a Slave, a very dark movie, but also very interesting movie. 12 Years a Slave, that's exactly the title of the movie, 12 Years a Slave, and you don't find it. And it's also, actually you do find it, second one, but first you get something else. Why? The 12 is just removed from the query altogether, because it's just numbers. That's how we did it for sake of simplicity in the first sheet. Then you have years, which is super unspecific, and then you have slave, which is also, you have a lot of movies about slavery. So, for now, we did nothing about these words occurring next to each other. So that's also something. People write a bunch of keywords. What do they actually mean? Should I consider this as a phrase or as unrelated keywords? You have to guess what the user means. So quite interesting, and you made that experience in the first sheet. Okay. So that was the first sheet, and if you have any questions, ask any time about your tutor. So you will get feedback on your sheet if you have asked for it. That was written very explicitly on the first exercise sheet. You have to ask for feedback and also say exactly what feedback you want, so that your tutor knows. And some people say, just give me a short feedback, give me more feedback, and so on. So today, after the lecture, Robin will sit down and work on assigning people to tutors, and then you have a tutor and they will try to give you feedback until Friday. So that's the instructions we give to them, so that if it's relevant for the next exercise sheet, you get it in time to incorporate it. So we do everything via the SVN. So you just do SVN update, you have your local working copy, SVN update, then you just, SVN in a nutshell again, like Git or any of these versioning systems, you have your local copy of the data. There's the data on the server. It works two ways. You can commit stuff. That's how you commit your exercise sheet. Just say latest version, but you can also get stuff. We have something new for you here. You get it via SVN update. So that's very comfortable, I think. Oh, by the way, Robin, do we have that already, these time slots? Or does should be? Not found? Okay, maybe we have to fix.
This link doesn't work, but everyone in their Daphne should have like a...
Oh, okay, it's on Daphne. Okay, so let me just fix that maybe on the slides. So you're saying it's on... See link when you log into Daphne? Yeah? Is that what you're saying, Robin?
Yes.
Okay. Okay, let's just fix that here. So when you log into Daphne, you should see and I'm not showing it now, you will figure that out. So if you want, there is you can come here, you can ask questions. There's the forum, and people use that where you can ask questions online. But maybe you want to talk to a person, and you can do that anytime. So there's just a tool where you click. It's really almost barrier-free. You just go there, you say, 10 minutes, 20 minutes meeting, and you will get a slot. And by the end of today or tomorrow, you will know who your tutor is. So now, before we start, as a motivation, so what's the exercise sheet for the next lecture? Let me briefly show it to you. It's here. So long instructions, but it's also not that hard. So now it's all about ranking. So for now, you just use the ranking from the input file. Now, and there's a formula called BM25 where you give words in text scores. And I will explain all this in a minute. Exercise 1 is just to extend your work with your code from exercise sheet 1. Whenever you work with code from a previous exercise sheet, you can use your own code or improved version of that code. You can also use the master solution if you prefer that. So exercise 1 is just extend your code by scores. We didn't have scores so far. Then exercise 2 is now you have a little search engine. How well does it do? We have files for you which are somehow queries with their ideal results. That's called a benchmark. And here we have a quotation mark that's not correct. We can't continue until we have fixed this. It's a major irritation. I can see it in your faces. So a benchmark, and the benchmark is not quite finished, so I can't show it to you yet, but maybe you can just imagine it in your fantasy from my description. It's just a query and the ideal result set for that query. So Oppenheimer and what you would expect. Indiana Jones and the 3, 4, 5 Indiana Jones movies there. And then you can run a little program which you should write, which just checks how well do I do compared to that perfect result. And how to do that, which metrics to apply, this is something we will learn today. And then now you have your little search engine with a ranking function, you have a script which evaluates it, and now you do something which is very typical for research. You tweak your parameters, because this ranking function has some parameters, and now you try to improve your engine. And for that, we give you a training set, so some results where you can just tweak. You try to get better results on this training set, and then at some point, this is how it also works in competitions. At some point, you have to say, okay, now I'm done tweaking. That's my final answer. And then you commit, and then you run it on a separate test, right? Of Of course, you are not allowed to fine-tune on the test set, and we will come back to that towards the end. That's also how you do it in real research. For deep learning, you have lots of these competitions which do it in a very similar way. You have a ground truth, you have a benchmark, you tweak on a training set, and then you run it on a test set. So, and let's dive right into ranking. No questions on the chat so far. Don't see any questions from the audience. I'll just ask any time. And first half of the lecture will be very lightweight. It feels a bit strange when all the doors are closed, and it's. I hope you're not falling asleep. CO2 levels are 904. So we are still surviving. So motivation. So a keyword query is a formulation of a search desire. So yeah, I just gave you examples. Yeah. So yeah, what you just get, you type a few keywords and you get text containing these keywords. Maybe doesn't mean it's relevant. Just because it contains the word doesn't mean it's relevant. Yeah. So relevant, when you do search engine, that's really the key concept, relevance, and that's what this lecture is about. For web search, it's particularly important. I mean, because you have millions of hits. The early web engines pre-2000 were really bad at this. That's why Google became so large, because they did it better than anyone else. But also, yeah, let's just quickly do that. I don't know if you've ever tried search on any web pages. Uni Freiburg is no exception. They are just as bad as any other. I don't know, what do we want to search? We can look for technische Fakultät, so Faculty of Engineering, random query. I mean, it's clear what you would expect. You would expect now you get, right, that's very typical. Okay, there's an event, celebration going to happen very soon actually, but that's not what you would expect the web page of the technical faculty there, right? So I always find this go to any website, even of well-known companies who have some internal search, and the search is just abysmal. I mean, this is just something, and it gives you some list, but the ranking is just very, very bad. It's basically unusable, which why everyone will just use. So if I do this here, Technische Fakultät Uni Freiburg, then I will just do it via. Okay, Google is also not perfect. That's interesting. Okay, interesting. Okay, so even the web search, that's I'm surprised. I'm really surprised. Let's try to find out offline why the ranking is so bad. So you see, ranking is a problem. It's a real problem, even for nowadays search engines. So how do we improve it? And here's the basic idea, and it's quite easy. So far we had these inverted lists, and I hope you still remember that from the last lecture. Now, so university is in document 17, 53, 97, 122, and now you also have a score. A score, and what does this score mean? It says university in this document is, in document 53, yes, it contains the word university, but it's not really about university. That's what the score says. Document 127 contains university, but it's not really about university. Think of the Toy Story thing earlier, right? The document contained Toy Story, but it just said this movie lost to Toy Story in some competition. So the document wasn't really about Toy Story, it just mentioned the words. So that's the idea of these scores. And the question is, of course, how do you compute that? It sounds like a very human and subjective concept. So Freiburg, the same, right? So here I have documents containing the word Freiburg, and only 34 is really about Freiburg, whatever that means. The other documents mention it, but maybe just in passing. So they have a very low score here. Now I get some funny sound feedback again. So Frank is here just for in case we get some feedback loops again. So let's just assume we have the scores for now. How do you operate with it? So now you have a query with 2 keywords. So what you simply do is add them up. Aggregate can also be something more sophisticated than adding them up. But for now, and that's actually a very common approach, so for now, just sum up. And I get some, for now, some, oh, now I get just sum. So do you hear a little, it's a very strange feeling today. The sound, the windows are closed, CO2 levels are rising. Feels like impending doom. I hope so. So aggregate is just sums. Let's just look at it. So 17 is contained just in this document, so it's 0.5. 23 is contained just in this one, it's 0.1. So do we actually have one? 53 is contained in 2 documents. So 53, 0.1 plus 0.2 is 0.3, right? So it doesn't even have to be contained in both documents to be contained now in the result. That's different from last lecture where we had intersect. That's now union. And now let's sort it by the scores. So now we can, that's ranking. So actually what's first now is 127. Why 127? Well, it has a large score in both documents. So document 127 is about university and also about Freiburg, so maybe it's a good hit for University of Freiburg. But 34 is next already, even though it does not contain the word university, but because it has such a high score just for Freiburg alone. So this can happen now, that's new compared to the last lecture. You can have documents, text records high up in the ranking, even though they do not contain all of the words. And I hope that became clear. That's a very important concept now, and that's still how you do it today for many search engines. For some strange reason, these things, so before inverted list it was just documents IDs, now it's pairs of document IDs and score, and for some funny reason they are called postings. You post something to a list, just accept it, it's called postings in the literature. And a posting, so posting is just a thing which you post it to the list, you send it there. It can also be more complex. Could also contain the information, oh, this word is contained in this document with this score at position 3, and more information. For today, for the exercise sheet, it's just document ID and scores, and I hope you can already see how you can extend your code from the last lecture. So now, so that's the approach now. You have these individual lists with scores. You merge them by just summing up, and that's also it's exactly what you do for the exercise sheet. And then you sort it. Let's very quickly talk about the sorting. These lists now can be very large, right? They will contain every document that contains at least one of the query words. Think about a web search engine. These lists will have millions, hundreds of millions of records. And now I want them sorted because I want to show the top ranked one, the top 3 for the exercise sheet. How do you do that? Well, of course you can just sort them, but sorting is, now you have a list of 100 million documents containing at least one of the words. You sort that, sorting is n log n. You learn that in data structures, algorithms and data structures. It's pretty expensive. So you only want the top 3. Actually, there are algorithms for partial sort. Yeah, we will not talk about that in the lecture. And then you can do it in linear time plus k log a. But you should just know that. So if you just want the top k, like the top 3 results, you can do it in linear time and not in n log n. N log n is really a problem when you have large data. Yeah, for example, k rounds of heap sort. If you want, for those of you for whom the exercise sheets are just too easy, try it. You can use heap sort or whatever. You can also use quick sort. There's an adaptation of quick sort where you, which gets this running time. You don't have to do this. You can. You can ignore this issue, but maybe you want to do it. It's interesting. So that's how we want to do it. Now, how do you get these scores? I just wrote some scores there, which maybe made sense, maybe they didn't. How do we pre-compute these scores? elusive. As I said, they should somehow say how relevant is, how much is university, how much is this document about university. Sounds like a very subjective concept, yeah, but we have to do it. How do you compute these scores? And there's a whole research area only about this, and I will give you a little glimpse now. So, term frequency. That's a very simple. So we are now talking about proxies for this relevance. If a document contains the word Freiburg 12 times, maybe it's about Freiburg, right? It just says Freiburg, Freiburg, Freiburg all the time. But some words are frequent, yeah, regardless of the contents. For example, the word the or doesn't really mean anything. So yeah, it's an idea, but also has its problems. Here's an example. So let's consider now somebody types University of Freiburg. People are doing that. And now we have a document 57, which contains University 5 times, Freiburg 3 times, and of 14 times. This document is really about of, right? So, and then we have this document 123, contains University only 2 times, Freiburg only once, but of, it just says of all the time, for whatever reasons. Why? Because of is just a very common word in the English language. Now I sum these up, as I explained before. This is 22, this is 26, so 123 is ranked before 57, right? You see the problem? You get it? That's a problem, right? So this term frequency thing is a good idea, but by itself it has this problem. Any questions about this so far, before we talk about the more complex stuff? So that should be clear. So term frequency, it is very often taken as a proxy for relevance, but then you have this problem with frequent words which don't mean anything. You want to disregard frequent words. So the next question is, how do I figure out whether a word is meaningful, like University in Freiburg, and just a word which, yeah, you want to say to the search engine off, just forget it. It doesn't mean anything. And there's another concept that's called document frequency, where you just look at how often does a word is contained overall. And let's look at these numbers. Can you please tell me what's special about this number? 16384, does it look special to you? You can write it in the chat or just, yeah? 2 to the power of 16, yes, very good. You should know your powers of 2 as a computer scientist. Yes. How about this one, 524? And a spoiler alert, it's also a power of 2. Which one? You can figure it out by some. Let's maybe do this one. 1024, you should know. What is it? Somebody else? 2 to the power of 10, yes. And if you know that that's 2 to the power of 10 is almost 1,000. That's why you have megabyte, gigabyte, and maybe byte. Yeah, you always have this. Is it 1,024 bytes or 1,000 bytes? So given that that's thousands, what's that? That's 500,000, yes? 2 to the 19, yes. 2 to the 20 is 1,000,000, and that's about half. So if you know that it's a power of 2, it's 2 to the 19. And I'm just doing that because you will see a log 2 in a second. So what do we have here? Of is contained in half of the documents, not surprising, right? If you have text, will probably contain the word of. Freiburg is pretty rare. Yeah, it's a very specific word. Let's just say it is. University is contained in a few more documents. So this kind of, we can take this as a proxy now for, okay, if it contains, in every second document contains it, then it's not an important word. If it's contained so rarely, then when it is contained, it probably means something. So, and now you just take inverse document frequency, and let's just, So, yeah, if I just do so, n is the total number of documents, and let's just, so this number we already saw, that's now 2 to the 20, almost 1,000,000. Yeah, and now we have, so I wrote the numbers here. If we take university, that's now, yeah, let's just do let's just do the math to check. So this is, it's log 2 of, so what do we have here? We have n, which is 2 to the 20, and divided by, which is when you do, it's minus, and df of university is 16. Yeah, so we have this here. It's a bit small font, but you will later see it. So it's 2 to the 20 divided by, maybe let me write it like this for the first thingy, and just check it for the others, whether it's correct. So it's 2 to the 20 divided by 2 to the 16, 2 to the 14. No, something is, 2 to the 16 was actually wrong, right? I think it's 2 to the 14. Please correct me if I'm wrong. 2 to the 10 is 1,000, and then times 16, and 16 is 2 to the 4, right? Do you agree? I hope you're all paying attention. Does anybody, I again get some? 2 to the 14, yes. Oh no, it's no reason to be. Everybody should pay attention. So it's 2 to the 14. So we have 2 to the 20 divided by 2 to the 14. That's 2 to the 20 minus 14. 2 to the 6. Log 2 of 2 to the 6 is 6. Yes? And the other ones you can check it yourself. And it does make sense. So you just kind of do the opposite by taking 1 over and then log 2. So what do we get now? What is this? This is 1. It's now a very low number because it's so frequent. This is a very high number because this is so rare. So IDF just says IDF is high when it's a very rare word and low when it's a very infrequent word. And why do we take the log 2? Now we get numbers which are kind of in the same range, 6, 1, 10, right? We don't want numbers here like 1 million versus 1,000. That's too big of a spread. It's a very common phenomenon that you want to measure something, but you don't want the spread too big. Yeah, maybe you want to measure popularity of a page. You don't want popularity 2 and popularity 1 million. That's too big of a spread. You take the logarithm, then it becomes a smaller range. And that's why we take the log. So it's a very simple principle. In IDF, you will see that everywhere. Even now today with all the learning stuff, that's a very common proxy to measure this. And now let's just do this here. So that was our earlier example. And now let's just add here the IDF scores, and I hope you remember them from the previous slide. So IDF of university was, what was IDF of university? 6, that's correct. So if we play a little memory here, we had IDF of which was 1, yes. So very low because it wasn't contained in half of the documents. And then we have IDF of Freiburg, which was in our example very rare word. What did we have there? 10, yes. So kind of if Freiburg is there, and now we just do that. So let's just do the math here. So 5 and 5 times 6, right? That's what we do. Let's just write it for some numbers here. So this is just now, this is the 5 from above times 6. This is just the 14 times 1, and this is just 3. So Freiburg occurs here 3 times, but it's a very important word, or IDF is high, so 3 times 10. Let's also do it for the other thingy here, so that's 2 times, it's 2 times 6, wrong color, 2 times 6, 2 times 6, this is 23 times 1, so no boost for the off. And this is 1 time, so it occurs once, yeah? So this says 123, Freiburg is just occurs once, just mentioned once, but because it's such an important word, it probably means something. That's what we are saying here. And now we can do the same game again. This is exactly Not exactly, there's yet another variation of it, how you do it for the exercise sheet. Now we just do the math, 74, 45, and now 57 gets ranked before 123. So that's the whole idea behind these kinds of ranking, and that's a very, very, very common principle, and how you still do it today. And if you do that properly, you can get really good rankings. Any questions? Yeah, 2 to the 14 was the Zoom chat found it. Okay, great. Any? Yes, sure.
What if in Word it occurs in every document?
Okay, that's a good one, because then the log 2 is 0, right?
Yes.
Yeah. We just have to define that.
So should you set the minimum to 1?
Yeah, let's just, it's a very good comment. Yeah, let's just, if, it's very rare, one should say, but yeah, it's a very good point. So if df equals n, let's just say then idf. Let's just define it as, or let's make it a bit more general. So this is a border case, but you're absolutely right to point this out. If, let's just say if it's more than n over 2, we don't do anything different. We just say it's 1. We don't distinguish between, because otherwise you will get strange things happening as well, right? It would, yeah, the numbers would get negative or something like this. No, they don't get negative, but they. So let's just go on. So here's some more. So one more variation of this. So here, so that's already a good one. So we do TF and IDF, and that's a very. And now we do one other variation of this. But before, this looks good in this example. What's the problem with this one? Here are a few problems. So the IDF part is actually fine. The TF part still has a few problems. So one thing is, let's assume you have a short document, 3 sentences, and we did have that for the movie descriptions. Some rarer movies are short. Some more popular movies have a very long description. If you have a description that 10 times as long, it will contain every word 10 times more, right? So just doing a TF without taking the length of the document into account is not, you should somehow take that into account. A document that is longer will just mention words more often just because it's longer. You should somehow normalize for document length. And now even if they have the same length, saying that just because it contains the word twice as often, that it's twice as much, that's a bit too much. Experience shows that you want to tune that down. So if it contains the word twice as often, maybe, yeah, it's a bit more, that word is a bit more relevant, but not twice as relevant. So you just want to tone that down. So just experience shows that. And this is a very famous formula. It's called BM25, which is a super weird name, but computer science is full of weird names. It took me years to understand why it's called BM25. It's just BM is best matched. So there was a research group or a whole area exploring these formulas like 200 years back, and they just tried a lot of stuff. And then so they tried BM1, 2, 3 or whatever, and MC13. And at some point BM25 just beat everyone. So they won in competitions 1 year after the other with this magic formula. And then it just stuck. So it was just internal code name for a formula, right? It's programming language C is called C because it's the successor of B. And there are a lot of such stories, like funny names, and which just stick and nobody, BM25. So, and now I will tell you how BM25 works. And it just works like this. It has the IDF part, but the TF part, you just modify it. And let me just say you this before I explain it to you. If you go back 200 years and read the literature about BM25, it's enormous how much there are whole articles, journal articles, 50 pages about BM25, but it's typical academic overkill. Actually, I can explain it on 2 slides, which I will do now. Lots of theory, and yeah, there are people who have worked on this for 10 years, so they are inflating it a bit. We don't do inflation here. That's the formula, and that's really all you have to understand. So you take the TF part, and then you have this, and we will understand this. That's what we will do before the break. We will understand this part. So there's a parameter K, and there's a parameter B. And B, this is for document length normalization. This is what I said earlier. If a document is longer, so you should somehow account for this. And don't worry if you don't understand this formula now, that's normal. Why does it have this particular form? This is exactly something we will explain on the next slide. So there's parameter K and there's this parameter alpha. And there are also these famous standard settings. This is, you still have that in deep learning a lot, by the way, where it says, oh, you have to set the learning rate to 0.1725. Then it works really well, believe me. And this is how it was for BM25. They set it to 1.75 and B to this, and then it always works well. So you have these magic parameters. Still a big issue in learning today, right? You have any methods, they have some parameters, and now you have to tune them, and they make a huge difference for how well it works. So let's just look at 2 special cases to understand this a little more. And let's just start here first. So let's set k equal to 0. And so what happens if we set k equal, let's just do that. So if we have, if b is equal to 0, let's do that here. Then what is alpha? You tell me what's alpha if we set b equal to 0? 1, yes, it's just 1. So that's like a correction factor, which just happens to be 1 then. So b equals 0. It just says basically how much should I normalize by document length. If I say 0, it says don't normalize by document length. So then we just have alpha equals to 1. And let's just look at the TF star part here. So if k is equal to 0, b is equal to 0, so alpha is 1, we have TF times, and now we have k plus 1, so 0 plus 1, divided by 0 plus TF. And what's this? What's this? Oh, we're approaching CO2 levels are rising. It impacts thinking ability. What is TF times 0 plus 1 divided by 0 plus? It's, I think it's 1, yes. It's 1, yeah? Or, but let's also clarify, if TF is 0, then TF star is also 0. So this is only if it's, if TF, because you're dividing by 0 here, right? So if TF is 0, this is also 0. Let's just do k equals infinity. So what do we have then? We have, how do we do that? So let's just write it like this again, k plus 1 divided by, the alpha is 1, k plus TF. Now we have the k here and the k here. Let's just divide by k on both sides. So let's just divide by k here. So that's 1 over k, the numerator and the denominator, divide by k here. So we have TF divided by k. And so what happens now if k goes to infinity? This is now TF times 1 plus, this goes to 0. And this goes to 0 as well. So this just goes to TF, yes? So also for, so this is for TF not equals to 0. When TF is equal 0, this should also be 0. Let me just clarify that again here. Otherwise, this wouldn't make sense. So if TF is 0, a word doesn't occur at all, then TF star is also defined as 0. And then maybe we don't have to write that here. That's like a special case, because otherwise you're dividing by 0. Yeah, so we have these two special cases. So if I set k, so that's kind of what the parameter k does. If I set it to 0, then I have binary. Even if the word occurs more often, tf, yeah, the score is always 1. And if I set k to infinity, then yes, if it occurs, I just have tf. And in between, it's just toning down the number of occurrences a little bit. Okay. So, and now here are some, yeah, and let's just do those. These are a few. You have a question or comment?
So K is how much each occurrence weighs.
So TF is really counting how often the word occurs. And so if it occurs 10 times versus 1 time, your score will be 10 times higher. And the question is, do you want it to be 10 times higher? If you set k equals to 0, it doesn't matter how often it occurs. You just count it as 1. The higher you set k, you more take into account how often it occurs. Yes?
Is B between 0 and 1?
B is between 0 and 1. Yes, I should say. Otherwise, this doesn't make sense. Thank you. So B is from, haha, wrong color again. B is from 0 and 1. Yes, this is kind of a convex combination. And then, Franco, do you also hear that? There's sometimes these funny effects. It's probably, I think it's just an alien invasion. Nothing to worry about. It will happen sometime anyway. Why not now? So, let's just do that. Here's some funny properties. And let's just, how do we do it? Let me just... Let's first do one thing to verify these. So these are 3 properties which we now prove. So one is, this is 0 only if this is 0. I claim that if TF increases, then TF star also increases. And if TF goes to infinity, TF star does not go to infinity. That's also what we want. And it goes to a fixed limit. So let's just, again, wrong color. Let's just... TF star, let's just write that again. That was TF, and let's set alpha equals 1 for this slide here. So this is, what was it? It was 1 plus, yeah, it's there. It's k plus 1. Let me just write this here. And please pay attention that I don't make a mistake here. K plus 1 divided by, and I take alpha plus 1, k plus TF. And now I want to see how this changes when I change, when the TF is varied. So let me just change this a little bit. Let me just do it like this. TF times K plus TF divided by TF times K plus, no, I don't want that down here, just up there, I'm sorry. K plus TF. So I have this now. Now I just divide by TF in the numerator and the denominator. So I get K plus 1 here, and I get K over TF plus 1 here. So, yeah, is that correct? I hope it is. I just divide by TF here. Yeah, I just TF. We have to make sure that it's correct. Okay. So let's just write that here and now check the individual properties. So here we have TF star is equals to, let's just copy that from below, K plus 1, K over TF plus 1. Yeah, and this is, I think this is clearly greater 0 if TF is greater than 0. This does not become 0 unless TF is, when TF is 0, we just define TF star as 0. It cannot become 0. Otherwise, let's just look at, let's just write it here again. k plus 1 divided by k over tf plus 1. Yeah, and yeah, you can actually see it here if it, let's just write a check mark here. Yeah, why? Because, I mean, tf, the way I've transformed it here, tf is just here, so it's in the denominator, and there it's again in the denominator. So if this increases, right? If you write it that way, it's clear, because it only occurs one. Yeah, it's twice in the, and let's write that again here. Okay. Plus 1, and let's just see what happens when you let tf go to infinity. So if tf goes to infinity, what happens? What's the limit if tf goes to infinity, if you look at this?
K plus 1.
Yeah, k plus 1, exactly. So this thingy here goes to 0, right? So this whole thing is k plus 1 over 1. And so this is also something. So k plus 1, the parameter k just tells you as tf becomes larger and larger, that's basically the upper limit, where tf star will never become larger than k plus 1. Okay, and the whole point, I think BM25, that's, if there's a whole literature, hundreds of papers, you don't have to read it. Basically, what you want is, you want a formula with these three properties. You want a formula that, yes, it's 0. You want a variant of tf, which is 0 if tf is 0, but not otherwise. Otherwise, it's non-zero. You want it to increase if tf increases, and you want it not go beyond a certain limit, which are very natural properties, right? You don't want tf to become arbitrarily large. And if you want that, that is just the simplest formula which does it. I think that's all the theory you need. You can throw away all these papers. This is just the simplest formula which has these three properties. I've now summarized 20 years of research on BM25. Yeah. And this alpha, yeah, I think that's... alpha is just... we don't have to talk too much about this, right? If you do DL over average document length, then you just say, oh, this document is twice as long as the average, so let's just take 2 as a factor. That's a bit too extreme, and now you do a linear combination between not taking it into account at all or taking it into account. And B is just something between 0 and 1. And this is what I just say. Yeah, you find a lot of theory. Academics like to do that. They like to do theory for stuff for which you actually don't need theory. But let's not get into that. And break will coming up soon. CO2 levels are 1707. We need a break, but 2 more slides. So you have to implement it for the exercise sheet. And let me just show the exercise sheet real quick. So that's the first exercise. Take your inverted thing from the first exercise sheet and just implement BM25 scores. So that's what exercise 1 is about. And how do you do that? So you start from TF scores. So let's just go back one slide again, and just to explain this. Where's the formula? Yeah, that's the formula. So BM25 is, you need the IDF part. So that's, let me just write that again here. You need the IDF part. Yeah, this was the IDF part, so you have to compute that. And then you need the TF star part. Now the TF star part is easy, right? You just can compute it from TF. If you have TF, you can compute TF star. That's trivial. You just multiply with that number. But you do need the document length and the average document. So the question is, how do you compute this IDF part? That's really, and let me just give you some, and do it, because you will learn something. So TF scores, you have to compute those. We kind of did that in lecture 1 already. Do you remember in lecture 1? When a word occurred 4 times in the document, we just pushed it 4 times to the inverted list, right? It was just there 4 times. All you have to do, instead of pushing it again, you just have a score which you increase by 1 if you push it again, right? That's all. So instead of having 23, 23, 23, you will just have 23, 3. That's easy to do. You will figure it out. While you're doing that, you're processing one document after the other. It's very easy to remember the document length for every document. Yeah, you're processing them one after the other. Just remember them. After you've processed all the documents, you just sum them up. You compute the average. That's also easy. How do you measure document length? Actually, it doesn't matter. You can measure it by number of words or number of bytes. Do whatever you like, or what's written on the exercise sheet. And now you need a second pass over the inverted list. Now you have your inverted list with TF scores, and now you want TF stars times IDF scores. And you just need one observation, and that you should understand, and you will learn it when you do the sheet. You have to replace TF by these scores. So what you need is the DF, right? So the TF you have, K is just a parameter, the B is a parameter, DL and FDL is easy, so it's really the DF part. How do you get the DF part? Yeah, the DF part is just the length of the inverted list, right? Go to the last exercise sheet. Let's just go to that slide once. Oh yeah, I want to keep. Did I kill all my annotations? I hope not. No, I didn't. Let's just go to this is something you should understand. Let's just say that's my whole inverted list for university. 1753, 97, 127. In how many documents does it occur? That's DF 4. It's just the length of the inverted list. So you know the inverted list length, so you know DF. It's actually very elegant, and you will realize this. So if you don't think, you would actually do something much more complicated, but it's actually very easy to do it that way. So, yeah, there are these 2 parameters. It's the point of the exercise sheet to play around with them. Yeah, here's some more things. That's also the exercise sheet. So you have this formula, you have these parameters. Now there are other things. Maybe you want much more. You say, oh, I have more ideas for my ranking formula. And you are very welcome. We have a little competition to incorporate them. So for example, so now we said that you can have results where one of the query words is not contained. Maybe you want to say, oh, if I have a document which contains all the query words, I want to give it a boost. Maybe a good idea, maybe not. Maybe you want to take the popularity into account. We gave you scores in the documents, right? Yeah, so you could take that. I will you will see it on the slide. And this is just the last comment before the break, and please do ask any questions if you have some. So query logs are, of course, that's what the big search engines do. You don't have query logs, can't take that into account, or learning methods. But yeah, this is something out of scope for now. But for the exercise sheet, think about boosting certain results, taking the popularity scores into account, which we have given you. This is something which you might want to. Let's just quickly go over the exercise sheet before we have the break. So you compute the BM25 scores, you write this evaluation script, and this I will talk about in the second part of the lecture. So now we let in some air and we have a 10-minute break. See you after the break. So we are all back, let's continue. So someone of you pointed out, very correctly so, and let me just rectify that, because I was confused, as were some of you, that actually this formula is perfectly fine when df is n, so we don't need that. This, let me just clarify this, that we don't need that. So df, if df is n, then idf is 0, which is fine. Which is fine. Okay, you don't need a party, you need one person being loud to be annoying. Let's just close it for now and open it as soon as we can. Yeah, this whole building is just the construction. So if df is equal to n, you have n over n. I was just confused. I thought it's log 2 of 0, but it's log 2 of 1, which is 0, which is perfectly fine. If a word contained in every document, there's no information. You just act as if it would not be there. Yeah, you just add some word to every document. That's fine. So let's continue. But it does feel strange when the... let's open it in 2 minutes again and try again. So let me continue. So evaluation. Let's talk about evaluation now. Now we have all these ranking functions, TF, IDF, TF star, IDF, BM25, and there are more ideas which you might want to incorporate. Now you have to test this somehow. Very typical setup. You have your system, you tuned it, and now you want to check how well it does. Of course, you can just do a few example queries and play around with it and get a feeling, but you want to do that more objectively. It's a very, very important part of research. And how does it work? You have a ground truth, and the ground truth looks as follows. You have a set of queries, for example, matrix movies, and you expect the 4, or maybe now it's 5, I'm not sure, matrix movies, and they have these document IDs. So that's, and let me just, we have built a benchmark for you, which was actually a lot of work, so Robin has done it based on work previous assistants have done. Let me just show it to you. This is how it looks like. So you have a query, films shot in Canada, and these are your relevant document or record IDs. These are the line numbers in the file from which you read, right? Movies which won an Oscar, and the relevant movies are 2, 3, 5, 6, 7, 8, 9, 10, and so on. Yeah, no coincidence that it's the low numbers because they are measured by they are ranked by popularity and so. Films where Morgan Freeman played a role. You get the idea. This is called a benchmark, and we have prepared them for you. And we have prepared one for training. This is this one, and one for testing. And we still have a little problem. So films shot in Paris. You see, a lot of films were shot in Paris. So what Robin did in the last week is just sitting down, going through all 125,000 documents and just watching the movie and figuring out whether it's relevant for this query or not, right? So amazing work, Robin. So unfortunately, Robin has not finished watching all the movies yet, which is why he still needs another half day to finish the benchmark. So what I showed you still has some small mistakes, so just wait, but you can already start with the exercise sheet and do the first part. You only need these data sets for exercise 3. So these will be there in the evening. Just hold on. So I think that idea is clear. And now, so you have your little search engine, you have this benchmark. Now you just, the idea is clear, right? You just give your engine matrix movies, see what result it gets, and now you have to compare it to that result. And now you have to quantify, okay, this is the result I got, this is the ideal result. You have to give a score which says, yeah, that was great. I mean, of course, if it's exactly that set, it's perfect. You have to give that a number. And this is the rest of the lecture. How do you quantify that? And this is, and let's start with some very simple, and let's just, so here's an example. Let's say our query is matrix movies. These are the 4 relevant documents, and let's just, so this one, and this is what our engine produced. And this is, and pay attention that I make no mistakes. So 17.5, they are not relevant. This one is relevant. And this one is relevant, and let's just say So 17 is not relevant. Let me just write it as not. 5666 is not relevant. This is something we have seen, right? You get a mix of relevant and not relevant ones. And then there's a fourth one which just is not in your list at all, right? That can also happen. 877 is not contained in the list at all. So let me just, 877 is, how do I write that? Or do I have it on the, let me just, 877, it's not in the list. Yeah, your search engine, maybe it does not return some relevant documents at all. And we use, I have a thing today with clicking. Oh, but I do think it's actually, I know why it happens, because the pen is not calibrated, but I will figure it out. There's a reason. I just realized by looking at the dot that the dot is 1 centimeter to the right of where I put it. That's why I always chose the wrong color. So there was a reason. It's not only dementia, it's also an uncalibrated pen. Yeah, you're laughing. That's a real thing. So P at 1, that's very easy. Let's, P at 1 is, you look at just the first document, and you look at how many, it's just a percentage among the top K. Let's just look at the first document and how many of those are relevant. And that's, let's just do that. So that's 1 over 1 is 100%. And let's just write it as a percentage. So precision at 2, you look at the first 2 documents, and you look at how many are relevant. So this 1 over 2, of the first 2 are relevant, so precision at 2 is 50%, or just 1, or just 0.5. Precision at 3, your turn. What's precision at 3? This is the result list. Yes, you can also write it in the chat, or just shout it. Precision at 3. 1/3, yes, it's 1 out of 3. So it's actually not good, right? The top 3, only 1 is relevant. And 1, let's just round it to 33%, or 0.33. What's precision at 4? Half, yes, 2 over 4. And that's 50% again, so you see it can go up and down. And now we do, what's precision at 5? Yeah, 3/5 exactly, 60%, right? So this is how precision at something, so 0.6. Yeah, and just, and then there's P of R, which is just P at, so that's a special P at R, and R is just the number of relevant documents. So in this case, so let's just do P at R. So P at R is one of the P at something, and it's the something where the something is the number of relevant document, and you just... So what is R in our example? It's a number. What is 4? Yeah. So P at R in this case is just P at 4, and P at 4 was 50%. So that's it. Simple enough, you just have to know it. Let's just continue, and you ask questions if you have any. So that's precision. Now there's average precision. So precision as a parameter at K. This is very important for web search and for a lot of searches where you only want to look at the top of the list. The top of the list should be. So these numbers are extremely important for web search engines. Average precision looks at the whole thing. And let's just do that, and let's do the same thing here. I will explain everything, don't worry. So now we have, so the first one is, this one is relevant. I think it's the same as before. This one is relevant, and 10 is relevant. And then we have 877 somewhere back here, relevant. let's just say it is contained in the list. This one is not relevant. Let me also write that here. And you tell me when I make a mistake. And let's just, let's assume this is, let's just put the ranking positions here. This is the first document, the second document, the third, the fourth, the fifth. And let's just imagine this is the 40th. So actually the fourth relevant document occurs in my list at position 40. So now I look at the position of the relevant documents. The top ranked relevant is at 1. Then I have one at 4, at 5, at 40. 1, 4, 5, 40. It's just where the relevant documents are in sorted order. And now I just compute precision, like on the slide before, but I compute precision at the position of the first relevant one, precision at this one, at this one, at this one. So let's just do that. And let's maybe write the numbers. So that's the first one is at P at 1, which is up to you. P at 1. What? 100%, yes. 100%. P at, what's the next one? P at R2 is what? What's the next precision we have? That's P at 4. And what is it? 50%, that's correct. What's the next one? P at 5, that's where we have our next, and what is it? 60%, that's correct. And the last one is P at 40, and it is? 75%. What's P at 40? 10%, yes. It's 4 over 40. Exactly. 4 over 40, which is 10%. So now we have that, and now the average precision is just, let's just do that. It's just, we take the average. 100% plus 50%, and while I'm writing it, you compute the average of these 4 percentages. 60%, that's 210, plus 10%, that's 220, divided by 4 is 55, that's correct. You don't get a calculator in the exam, in case you were wondering. It's 55%, so average precision is 55%. It's important, we don't have it here in the example, let's just assume this relevant one is not in the list at all, which means it's like infinitely back in the list, and then I hope you see that this makes sense. You just say that it's 0. The precision is 0 at this thing. Right? The further this is back in the list, the lower the precision at this thing is. So we just treat it as 0. But that's very important, you take it into account, right? You can't just, if this were not in the list, just ignore it and just take the average of the first 3, just take this sum over 3, that would be unfair. You want to punish your engine for not including relevant ones in the list, right? If this would be not in the list at all, you would have a 0 here. And then it would be 210 over 4. Okay, you ask if there are any questions, otherwise I continue. Now we have a funny thing. So there's averaging happening here. That's averaging for one query, right? We have one query here and we compute average precision. Now I want to do the thing over many queries. Let me just remind you, here's a benchmark. Yeah, this is a benchmark where I have 28 queries. And now I want to compute the average precision and average over 28 queries. How do you call that? Do you call it average precision? No, you call it mean average precision. So mean is just another word for average. So you use the mean when you average over all queries, average when you average for one query. It's just a bit, you have to understand this. So yeah, so mean, yeah, MP at k is just for every query you compute the P at k and compute the average. That's simple enough. You can do that here. And if you do the average precision, which is average for one query over all queries, it's called mean average precision, MAP. It's actually a very famous value. You will find those in many Yeah, map is mean average precision. So you have average twice with two different words for the reasons I just explained. Now 2 more, and then that's already it. 2 more measures, and we do it together. And so that was a simple one, which I just showed you. Here's one, and 2 variants for things which you have often in practice. So far, let's go back to that example real quick. And also this is how we have it in the exercise sheet, a document. In the benchmark it says it's relevant or not relevant. That's it. Can we try opening the door once more, Frank? Okay, or any one of you? Let's see whether there's... No party. Wonderful. Quiet. Maybe I should also be quiet. Then we can have a little meditation session. So we have, it's just a document is relevant or not relevant. That's it. But sometimes in applications you have some documents are more relevant. Yeah, you say, oh, this is really relevant. This should be in my list. This is, somewhat relevant. This is not relevant. So you have shades of relevance. That's actually pretty frequent. And you can just give them numbers. Doesn't have to be 3 shades. Here it's 3 shades, could be more. For this example, not relevant 0, somewhat relevant 1, very relevant 2. Now, how do you compute a good scoring function? So you certainly want to give a bonus if you have a very relevant one. You want that at the very top, right? You want to award a search engine that puts the very relevant ones before the somewhat relevant ones, before the not relevant ones. And here's a very simple idea. Cumulative gain, you just sum up the relevance scores. So if you have very relevant ones in your list, that number will be larger. But that doesn't really award if it's higher up in the list, and that's why you have a discounted cumulative gain. And the most complex thing about this ranking formula is its name, discounted cumulative gain, DCG. It's also famous. And just understand the formula, so you just, and we will see an example in a second, you sum up the relevances of the documents in your result list. So it's clear that if you have very relevant ones there, this will be a larger number, but you divide it by, again, the log 2 is for not discounting it too much, just the rank where it is in the list. So if the I is high, this is further down in the list, then you divide by more, right? It contributes less to the score. So the best thing is to have a very relevant one. Let's just take, you have a relevant one at position 1, then you have a 2 here, and you divide it by log 2 of 1 plus 1, 2 by just 1, right? That's the best. Sorry? So this formula awards having very relevant ones, the more relevant ones at the beginning. It's easy to see that this, ideally you want scores which are in the range 0, 1, right? You want to say 0 is really bad, 100% is the best. We had that before. This score is not in 0, 1. So what you do for this scoring function is you also compute the ideal DCG. The ideal DCG is when you have all the very relevant ones, then the somewhat relevant ones, then the not relevant ones. You compute that formula for the ideal ranking, and then you just divide the one you actually have by the ideal, and then you have a number between 0 and 1. And let's just do that. So let's do the DCG at 5, and that's just, so what was the formula from the previous slide? Let's just, let me just, the formula was DCG, the general formula, DCG at K. Let me just do that. Different colors. You can already do it in your mind and k. This was sum over 1k, and it was the relevance of document I divided by log 2 of I plus 1. So we have, what do we have here? DCG at 5, we have a sum of 5, and I just write fractions here. That's what I'm doing. I'm just being economical here. So here I have log 2 of the first rank. It starts with I equals 1, is log 2 of 2. Here I have log 2 of 3. So this becomes larger. Again, the log 2, the purpose is, yes, it should become larger, so punish it if it's later in the list, but not too much. That's a very frequent reason for the log. Very simple. Log 2 of 6, and we don't actually have to compute many of these logs. And now here I just write that's just 1. Here I just write 0. And let's do it in red. 0, here I also write 0, and here I write 2 and 1. 2 and 1. Okay, I don't have to compute the logs where there is a 0 in the numerator. So let me just, so this one, log 2 of 2 is just 1. Log 2 of 4 is? Log 2 of 4? 2. 2, 2. 2, 2, 2, 2. Log 2 of 5 is first 3 digits after the dot is enough. Okay, yeah. Okay. Let's just, so what is it? Let's compute this, and equals to, someone, so this is 1. The first one is just 1, plus, this is 2 over 2, it's also 1, plus, and then we have this 1 over log 2. It's what?
2.35.
No, 1 over log, yeah, but and what is 1 over log 2.5? Okay, it's 2.35. Okay, let's just write it there, I think. .43? 42, of course. 42, okay. And so what's the log thingy? It was 2 point?
3, 4 approximately. Approximately
2.34. Okay, you get the idea. Okay, so we have this, and this is not normalized now. And now let's also do the IDCG thing. And that was, yeah, I have to do that real quick. And that was, so I have to, yeah, that's again log 2 of 2 plus divided over log 2 of 3 plus divided over log 2 of 4 plus divided over log 2 of 5 plus divided over log 2 of 6. Now what's the ideal ranking? You have to tell me what in the ideal order. What's the ideal order? What should I write for the numerators? What are the 5 numerators if the ranking is ideal? I need a sequence of 5 numbers. 2, 1, 1, 0, 0. Yes. 2, 1, that's the ideal ranking. And you can see that this gives the highest number, right? For you have 3 relevant documents, 1 very relevant one, 0, 0. And we also have to compute that. So what is it? So that's now 1 plus, yeah, it's 1. No, that's not 1, that's now 2, right? The first one is 2 over 1. And it's again the wrong number. It's not trivial, but I like a little challenge. So that's 2 plus 1 over, can you please compute 1 over log 2, 3, and I'm trusting you to do the right thing. And that's 1 over log 2, 4, it's 1 over 12, so it's 0.5. What's this? 1 over log 2, 3? 1 over log 2, 3, please. 1.5. Really? So what's log 2 over? It should be less than 1. Right? Log 2 of 3 is greater than 1, so 1 over, what is it? You don't have to do that in your head. Okay, so we can 1 over log 2 of 0.64, right? Round it up, it's 0.63, yeah, 0.63. So this is 2. Okay, so this is 2. No, it's actually 3.13, right? And I hope this is correct. And now we compute the NDCG. Yeah, and I should have used my space here a bit better. So that's now 2.42 times 3.13. And that's approximately, yeah, of course it's not correct now to work with the 2.42 divided by 3.13 is, yeah, around 77%. Okay, you get the idea? Any question about the NDCG? These are typical exam questions, by the way. Understanding these formulas, writing a little program that does it. Any questions about this before we go to our last ranking formula? So I think you get the idea. Yes, sure.
So I was wondering earlier why we start mixing from 1 and not from 0 as we used to. Is it because this mark plays out nicer?
Mm-hmm. Yeah, the question is why. I don't think there's a strong reason for that. So there's no particular reason. Yeah, why do you start here? I mean, you do want to. No, there is a reason. I mean, you don't want to divide by 0. That's a good reason, right? So you want to have these denominators here, and you want to start them with 2 is kind of where you want to start, because log 2 of 2 is 1. You don't want to start with log 2 of 1, which is 0. So I think that's the whole reason. But yeah, it's really a heuristic formula, which does something meaningful, and that's how it's used. And here's another one. That's the last one for today, and then just some general comments, and then we are done. This is a very typical situation, and let me just go to the example, and then back to the slide, and then back to the example, and again do it together. Just imagine, so Robin, I told you we had to watch all these movies, 125,000 of them, to do this benchmark, which is a lot of work. But now imagine you do that for the web or for even more movies. It takes too much time. So what happens then? That is, your ground truth is not complete. So you have a search engine and it returns something at the top, but there is no judgment. Like, you don't know whether it's relevant or not. So you have relevant and not relevant, but you also have don't know. And now the question is, how do you compute that? Now we have party again, but we try for a few more minutes. And here's the very simple formula. The formula is, and by the way, this happens when you do pooling. So you have a competition, 100 people are participating, and each of them, their search engines deliver results, and then, so you just wait for the results to come in, you take the top 10 hits from each search engine and just do the judging on these documents. So something like this, and then it will, so you just judge the top K results from each participant, and then you won't get relevant judgments from some, if you do that in a certain way. And now you have this formula, which is very intuitive, which is 1 over R sum over D RR1 minus NRD min Rn. And if you see these formulas for the first time, like BM25, you think, But with all these formulas, they just look scary, and academics like to make stuff look scary, but it's actually pretty straightforward, as we will see in the example now. This is always doing the obvious thing, in the kind of simplest formula which does it, which when you write it in math looks scary, but you will see that it makes a lot of sense. And let's just do it for the example, and then it becomes clear. So what we have is, we have the judged relevant documents, the judged non-relevant documents, the RR, and we will just do it, then it will become clear. Here's our example, and we will now go back and forth. Is it okay, or should we close the door? So we have, let's close it, and then try it like this. So RR, that's a set. It's a set of relevant documents in my. So that's 3 and 8. And as you see, these numbers are actually, I have a relevant one here and a relevant one here. That's just RR. Then I have the number of relevant ones. That's just the number of relevant ones in my list. That's just 2. It's the size of. And I have the number of non-relevant ones in my result list, which is just 3. And let me just. Oh no, that's not true, because I have, I forgot this, so I should rectify this here. In my example, this is what the search engine returned. It returned 9 results, but there's actually one more relevant one, which is not in the list. So my R is 2. And there are 10 non-relevant ones which are not in the list. So I have 3 in the list and 10 here, so this is actually 13. So that's simple enough to understand. And then there was, on the formula, there was this, the minimum of these two, the minimum of R and N, that was, and that's just 3 in this case. And why the minimum, we will see that in a second. And now, there was this NR thing, and I think I will maybe go back. I have to compute this thing NR, and I will go back to the definition in a second, for both of the relevant documents in the list. And what NR was, let's just go back quickly. NR was just those from the R top-ranked non-relevant before the ones, yeah? So I just look at basically I just look at the ones before that are not relevant, but I cut it off at R, and R is 3 in this case. So let's just do it here. So how many non-relevant ones do I have before here? So that should be punished. That's 1, so that should be 1 over, I think, and it's actually the opposite of that, so that should be N minus 1 minus, let me just, okay, this is, the NR over D, okay, this is not what I wrote here. The NR is just the other part, yeah. I'm sorry for going back and forth. I just want this one now, and that was just 1, okay? I'm sorry, just give me I will, so that was just, I think it's just a number of, that was just 1. There's just 1 non-relevant one before that, and that was, how many non-relevant ones are before that one? That's just 3. So I just count the number of non-relevant ones before here. And now I just do this thing on the, so there was this 1 minus NR over 3. And if you do it with this example, it's actually, and this is min of R comma N. And this is now just, I'm sorry, I should not have written the 1 minus in the numerator, but before that, this should be this. So this is now just 1 minus 1 over 3. So that's 2/3. And ideally that's not bad. If there were no relevant ones before here, you would get 100%. So that's the ideal case. You have a relevant one and no relevant ones before that. So that's the point of this whole measure. And here we do the thing with NR over 8 divided over the min thing, and I will explain the min thing in a second. Just understand the quality of the number. Here I have a relevant one, and actually I only have 3 relevant documents, and here I have 3 non-relevant ones before that. So this is punished, so I have 1 minus 3 over 3. So this contributes nothing to the score. Just 1 second, just to summarize this before I take the comments and the questions. So this one is pretty good, right? There's just 1 relevant ones before it, so it gets a score of 2 over 3. And this one is bad. There are 3 non-relevant ones before it. It gets the minimal score. It does not contribute to my score. Yes?
Didn't we say we cut it off at like R? So, I mean for NR...
yeah, didn't we say we cut it off? So the docs from the R...
like R is 3. So
R is 3.
Right?
Yeah, it's the R top-ranked non-relevant ones before D.
So we only counted non-relevant ones, and from those the top R.
Yes.
Okay. Not the top R, and from those the
No,
non-relevant.
no.
Okay.
That would be unfair. Yeah, I agree. It's a bit confusing, but yes. And we just do that if there are even more non-relevant ones, we don't punish that further. That's also the reason for the min thing here with R. So if there would be 5 non-relevant ones, we would also take it as 3 for the simple reason that you don't want the score to get lower than 0. So that's essentially what you're doing. And now you're just, so you have 2/3 and 0, and then you have one which is not in the list at all, and you get a 0 for that. So the overall score is just, that's simple enough. It's just the average of these. Oh my, I shouldn't have done this. This is bad. Oh, I see now that I have but I have an idea. I will just delete this stuff. I'm a professional. Bam. So I will, yeah. Now I just, and the bpref, so if you do it this incremental way, it's actually, of course you have to do this yourself once to fully understand it. But so the bpref value is now just the average of this, and the other one gets 0. So this is now just 2/3 plus 0 plus 0 divided by 3. Yeah, it's just, every relevant one gets a score. And this is a pretty bad ranking here. So this is 2 over 9. And 2 over 9 as a percentage is, that's your last math. What's 2 over 9? What's 1 over 9? Oh, you should know your fractions, like 1 over 7. This is something, you should do it as a daily exercise. What's 1 over 7? 1 over 7, 0 point. You should be able,
4, 3.
Exactly, very good. You can do these divisions in your head. 0.143. What's 1 over 9? No, 1 over 9. Yeah, it's 1 over 9 is 11, 0.11111, so this is 22%, exactly. Let's just go through the rest of the slides. So I will not just do it yourself. You have to do these things yourself to really understand it. I think you got the general intuition. Why the min? I just briefly explained this. Yeah, this is just some finer points. And this one, that's important. I just said it, right? If something is not, it would be unfair to just take these 2's and then divide by 2 for the same reason we had earlier. If something is not in the list at all, you should punish it, which is why there is a +0 here and divide by 3. So you should not just ignore the ones that are relevant and not in the list. They should be punished. You can read that on your own time. Few more general things, and then we are done. And please, if there are any questions, just let me know now or come afterwards. Overfitting is very important. So, yeah, why do you get two sets? Let me just say that again. It's a very, very typical thing. You have your function, you have these parameters, and you want to improve the parameters, right? So you can take this set and run your search engine with all kinds of parameter as often as you like on this set for the tuning, but then you have to test it on a different set, and you can do that only once. So you train, you tune as long as you want on one set, and then you evaluate it on the other set. Because if you do the evaluation on this set, that's kind of unfair, right? Then you're doing it's called overfitting. Maybe you have so many parameters that you can basically make it work perfectly on this training set, right? You could write a program that's perfect on this training set by just doing if query is equals to this, then output this. It would get a score of 100%, but obviously you're not doing what you should be doing, right? That's what you fine tune on one set and then you test it on the other. Let me also point that out on the exercise sheet. It's also very important for all the learning stuff and so on. So while you do the training, you don't look, of course we trust you to do this in a real competition, you simply don't see the test set on which things are finally evaluated. While you do the training, the fine-tuning, you don't look at the test set. And at some point you just say, okay, I'm done tuning, and now I evaluate it once. And then there is this table on the, is it there? Yeah, there it is. There's a little table, it's a wiki, you can just edit it where you can. So Robin put a result there, which hopefully you can surpass. You just put your results here, you say which parameters you took, which numbers you achieved, and what kind of stuff you tried. And then, yeah, it's a typical leaderboard thing. Okay, this is what is written here on the slide. Two more things before we are done. Should I explain them? I think they are not so, we are already a bit over time, but okay, let me at least say what's on the slide and not explain it in detail, just so that you can look at it. It's just for deeper understanding. Our ground truth were just sets, right? These are the relevant documents. We're just saying these are the relevant documents in no particular order, but your search engine produces them in a particular order. So it's kind of strange, right? You have a set as the ground truth, but your engine produces a rank list. And yeah, this is just explained here why that is so. So if you wonder about that, there are good reasons and they are explained here. I won't go through them, it's just if you are interested. Let me say it again. The ground truth does not give a ranked order of the thing. The ground truth tells you this is the relevant documents as a set, but your search engine produces a ranked list. And all the measures we have seen are comparing a ranked result list to a set. And why are you doing it that way? That's written on the slides. And just have a look at yourself if you wonder about that. And that's it for today. The exercise sheet, we explained it. You have to wait a little longer for the training set until Robin watches all movies. One more question before you leave. We're almost done.
So
Yes?
slide 22, just to make it sort of not some confusion. We say, hey,
Yes, slide 22. There's the yeah.
we say PR1 is 0 if it doesn't appear.
Yes.
Is that the definition of AP or an optimization of AP?
No, that's the definition. You have to take it into account, and it's 0. Yes. Okay, people are. Let's do the rest offline. See you next time. Have fun. Thank you.